Hi, and welcome to the CFE Media and Technology Education Session, Electrical Systems and Rooms. I'm your moderator, Amara Rasgus with CFE Media and Technology. If you're interested in receiving one AIA CES approved learning unit for this event, you'll need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Resources option on the left side of your screen. In keeping with the American Institute of Architects Continuing Education System Policy, please take some time to read the quality assurance slide. For a seamless online experience, here are some tips. First of all, the Q&A session with our industry experts will start in about 45 minutes, and that's at 1:45 Central or 2:45 Eastern, or immediately after this presentation ends. Attendees will receive an archived version of this session. You can see the Q&A details in the Meetings tab on the left side of your screen. Zoom invite details can be found in the Additional Resources tab under Q&A session. Additional resources can be viewed and downloaded on the left side of the screen under this session's agenda. If you'd like to take notes within this session, please click on the left panel labeled Notes to do so. The session is available on demand if you need to come back at any time. All right, well, here's a list of the learning objectives. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. There are also underlined hyperlinks to references and resources throughout this presentation. All right, now let's hear from today's subject matter experts. Brian Renner has more than 30 years of experience as a manager, director, and engineering leader in the design of numerous types of facilities, and he has a passion for mission-critical and science and technology facilities. He's a longtime member of the Consulting Specifying Engineer Editorial Advisory Board and has been contributing articles and presentations for the brand for more than 25 years. James Lessard is a licensed electrical engineer with about 15 years of experience providing engineering consultant services to both public and private sector clients. He has extensive experience in preparing lighting, power, communications, fire alarm, systems, and security improvements for a variety of project types and clients. These include healthcare, higher education, government, and so many more. Lessard is well versed in the pursuit of energy efficiency and sustainability initiatives and the pursuit of LEED and similar accreditations. All right, Brian, let's get started.
Thank you, Amara. As Amara mentioned, we have about a 1 hour or less overall discussion here. So we're going to try and hit the highlights. We're going to be referencing the National Electrical Code version 2020. Always check with your local jurisdiction what edition of the NEC they are using. We'll also be references to the International Building Code, and the same when you do your code analysis, check with your local authority and where your project is located. We're primarily going to be focusing on 800 amps and above and primary services. We're not going to get into small closets and locations for a single panel. We're not going to discuss hazardous locations. That is a whole topic in of itself on how to lay those systems out. And we are going to go beyond the NEC and talk about good engineering practices. Next. So really, electrical room design needs a coordinated team. It's not a architectural, electrical only, mechanical, structural. It really requires the entire team to work together to adequately design a room. And we're going to be touching on the electrical issues, things that are appropriate for your architectural partners to know, structural, mechanical, and fire protection. And the electrical engineer should try and take a leadership role in coordinating all these disciplines. Next.
So let's talk about the different types of interior electrical spaces that we might encounter during our design within a building. So of course we have our primary service electrical room where we bring our utility feeds into the building. We'll have electrical rooms scattered throughout the building if it's a multi-floor building on each floor, serving various areas. And we might also encounter a UPS or battery room where we've got a centralized UPS serving potentially IT loads or the like. And then if we've got NEC emergency, optional standby or legally required systems, or a hospital essential system, we may have interior generators as well, computer rooms, and utilities and vaults where we may have utility transformers or distribution transformers and primary switching equipment.
So let's talk a little bit more about some of the points for design issues and considerations. We're going to talk about working versus dedicated spaces. James and I will get into each of those topics and you understand the differences. Also, in terms of foreign systems, there's a lot of questions on what other disciplines can have piping through there. We're going to talk about that. We're going to talk about fire protection, fire ratings, when sprinklers are needed, and we're also going to get then into ventilation and cooling, a key issue in working with your mechanical HVAC engineers. Can't ignore structural leisure. There are structural concerns. We'll talk about building occupancy and briefly mention lighting. Next.
So as we work within electrical rooms, our design needs to be cognizant of some spaces that we need to allocate for electrical equipment. Two that are very important to electrical switchgear, switchboards, panel boards, and the like are dedicated space and working space. Now, there's different motivations for having these two spaces reserved within the electrical room. The dedicated space is primarily to serve the equipment. It's to allow conduit, an exit and entry point from the gear. It's really to serve the equipment in that installation. The working space, as the name implies, is really for working, for inspecting, for maintenance purposes, and those type of activities that are going to occur after the installation is complete. So the code dictates that we have these spaces. The dedicated space is the space that is defined by the footprint of the gear up 6 feet or to the bottom of structure, whichever is lower. And the working space is the width of the equipment. And then NEC table 110.26A1 defines the depth of that equipment. We'll get into that here in a little bit. That minimum working space width needs to be a minimum of 30 inches or the width of the equipment. So where does the working space, where does that requirement apply? Well, 110.26A tells us that equipment that's operating at 1,000 volts nominal or less that is likely to be examined, adjusted, serviced, maintained while energized. And that's really the takeaway. That's the part that should probably be underlined and bolded, is the while energized piece. And in practice, that typically is switchboards, switchgear, motor control centers, panel boards, disconnect switches, separately enclosed circuit breakers, motor controllers, controls for HVAC equipment, and sometimes transformers. The transformer is always a discussion. It's almost left open to interpretation by the local authority having jurisdiction. So you got to be careful about transformers and whether or not you need to provide working clearances in front of that equipment.
So when we talk about the amount of working clearances that we need in front or in back of the gear, the NEC provides several sections which talk about both the low and the medium voltage. I've combined them here into an easy to reference chart. They talk about the phase to ground voltages, as you can see there in the left-hand part of the chart, but I've included the typical system voltages that we almost normally use under those categories, such as 0 to 150 volt would be actually 120 to 208, 151 to 1000 is 480, 277. And then to the right, you'll see the conditions 1, 2, and 3, which we'll talk about in just a second, and how much feet and inches we need for each one of these voltages. And I've taken this all the way up to 34.5 Typically, most facilities that we're working in would only have up to 13.8 or 15 kV inside a building. Please understand, and we'll talk about this later, that these conditions, these clearances, working clearances, are the minimum. They're not necessarily the best or the clearances that you should have. I've also included the phase diagrams so you can understand how these phase to ground, phase to phase voltages vary between delta and Y. Next.
So as Brian mentioned, the working clearance depth is dependent upon a couple of different things. One being the nominal system voltage, but also a couple of different conditions. It's really about where the panel, the switchboard, the switchgear, where it's installed and what is directly across from it. So condition one, if you take a look at the side view on the left side of the screen, is depicting an insulated surface directly across from the panel. An insulated surface would typically be drywall or sheetrock type installation. Condition two being a panel board or switchboard or switchgear directly across from a grounded surface, such as masonry, concrete, let's see, block or tile. And then condition three is the condition where you've got a panel or a switchboard across from another panel or switchboard, where the condition is such that you could have exposed live parts directly across from each other. And so you can see in the table at the top of the screen how that impacts the required depth of the working clearance in front of the panel, or between them in some cases. Now, sometimes, dependent upon the manufacturer requirements often, gear will require rear access. Sometimes this is to get to non-electrical parts. For example, replacing an air filter on the back that needs to be changed on a reoccurring basis. If that's the only reason that we're needing access to the rear of the gear, then code requires that we have a minimum of 30 inches horizontally behind the gear. But if there are needs to get back there for inspection or for termination of cabling and the like, then the clearances that we previously discussed out of NEC 110.26A1 would apply, similar to the front of the installation.
So let's talk about dedicated spaces. This is distinct, as was shown in the diagram, from working spaces. It applies to all switchboards, switchgear, panel boards, motor control centers, shall be located in dedicated spaces and protected from damage. Examples are switchboards, switchgear, panel boards, and motor control centers. So we go to the next slide. So here's an example. We talked about this dedicated space, kind of the no-fly zone, the area above the gear. This is dedicated to the equipment itself. Where the workspace is for humans, this is really in regards to the excuse me, to the equipment. So can you have foreign systems? That's a common question. Mechanical ducts and plumbing in your electric room. The question is yes or no. It really is whether they're going over the dedicated spaces, and whether they're isolated by distance, a structural ceiling or a suspended ceiling, so that it's not dripping on the gear, it's not impeding entry into the gear for working maintenance, not necessarily maintenance, but future access space. And sprinklers, another common thing. Sprinklers are the one thing that you are allowed to have in the dedicated space. This is different from ducts or a drain running through or a plumbing line, which generally is not good practice to put in the dedicated space, but have to be located above it per NEC. Sprinklers are allowed. We're going to talk a little bit also about best practices with regards to this. It's not uncommon for the architects to want to lower the ceilings in the electrical rooms. So even though it says 6 foot or bottom of structure, what if the architect locates the bottom of structure 12 inches above your gear? Is that a violation of code, or is that more just poor practice because you got to get your conduits out of the gear and be able to do both the install and future work? So it really is more of an issue of good practice. Next slide. So the key classifications, when we go back, we talked a little bit about the different types of systems, types of gear. The key classifications affecting how you're going to lay out the electrical room. Are you doing low voltage? We saw the table with the different clearances based on voltage. Are you doing medium voltage? That brings in an increase in that working space, not necessarily in the dedicated, but in the working space clearances. Are you doing normal, standby, or emergency? James mentioned this. Emergency rooms are completely different requirements than just a standard normal power room in terms of what can be in there and what cannot be in there, and the types of fire protection. Also, equipment types. We're going to talk a little bit about types of equipment and how that affects the electrical design. We've already briefly touched on that. And then the heat and the temperature range of the space. Next slide. So let's talk about a few of the pieces of equipment and how they affect what you're going to do in an electrical room and how much clearance you will need. We talk about panel boards. We're all familiar with these. The NEC used to classify things as branch and circuit panel boards or lighting panel boards and distribution boards. They now just call them panel boards, but I think for the purpose of this presentation, it's good to consider them differently because they do require a different consideration. Your typical panel boards, like you see there in the photo, are wall mounted. They can be surface or recessed. Sometimes you'll see those in the hallway. Very typical for lighting and receptacles. The only thing you need to know about these, in addition to the normal clearances, is there is a requirement in the code that the swing of the door be able to fit within those spaces. And it's not a problem with branch circuit panels. Next slide. So now we're going up in size, and what used to be called and what I still categorize as distribution panel boards. These are typically from 600 to 1200 amps. They're going to feed large mechanical equipment. They would probably feed other branch panels, lighting receptacle branch panels. These are typically not recessed in a wall. They're surface mounted, they're deeper, they're bigger, they sometimes sit on the floor. And when you're specifying these and laying these out, most people in Revit have these laid out per size, per rating, so that you know that the dimensions, but understand that these will require specific considerations on space and working clearances. Next slide. So then we get into switchboards. Switchboards are different than switchgear. So what is a switchboard? Switchboards are normally available in 1600 to 6000 amps. That 1600 is a key thing. Understand that the panel boards are only going to go up to 1200 amps. If you start needing a 1600, you're going into switchboard construction. So again, these are going to be much larger, almost universally floor mounted. They don't have typically draw out breakers. That's an option in some models. They're normally fixed, so you're not going to have to deal with that clearance of drawing out a breaker. On most of these types of gears, rear access is not required. So you can mount these up against a wall, and the clearances that you need to work with are only in the front, possibly the side, but usually in the front. And they usually have compartmentalized construction. Next. So let's talk about switchgear. Switchgear and switchboard are often used interchangeably. There's a whole presentations on these types of topics. But switchgear is typically going to be draw-out construction. The breakers are going to it's going to require rear access to do terminations of the cables. And they have compartmentalized construction. And again, like the switchboards, they go up to a 6000 amps as well. The 6000 amp breakers do require additional internal cooling fans, but those are available. And these will, when you got to take all that into consideration when you're planning your room in the early phases of design. Next. So there's all types of transformers. On the left there, you see your typical dry type panel board that'll be feeding receptacle, branch panels, lighting panels. Sometimes these are stacked. We're often given very limited room in the design of these buildings. On the right, you can see, top right, you can see a dry type larger transformer. This is typically a medium voltage, 15 kV to 480 type transformer. And then on the lower far right, you'll see an oil type transformer, which may require containment systems. Now, there are all types of oils out there. Mostly we've moved to safe type oils, but the local authority having jurisdiction may require kind of a small bathtub be constructed for oil spill containment and how you deal with those in terms of not making sure the oil doesn't go down some floor drain. The thing about transformers is this is where your HVAC guy and even your structural are. You're going to have to talk to them, particularly on the large medium voltage type transformers. They're the ones that put off the heat in the room. They're the ones the engineer's going to want, HVAC engineers want to know how much BTUs it's putting out. Your structural engineer, these are very heavy when they get into these, and probably the heaviest piece of equipment, not only from sitting in the room or up on upper floors, we have to talk structural, but you also have to think about getting it in and out of the building in during the construction, and if ever has to be replaced. They're very heavy. Next.
So to continue our discussion on distribution, we also wanted to include electric vehicle charging stations, as these installations are becoming more and more prevalent, specifically on projects that have LEED accreditation aspirations or other green initiatives. So NEC Article 625 governs the installation of electric vehicle charging stations, and these installations can occur in either indoor or outdoor locations. I've got a project here with a local utility company, and they've got a fleet vehicle facility where they park their electric fleet vehicles out in the parking area, and then they service them within an interior building. So in that specific example, we've got electric vehicle charging stations in both locations, indoor and outdoor, and each have a slightly different requirement for mounting height. Outdoor requires 24 inches above finished grade, and indoor 18 inches above finished grade. With these types of installations, as with anything electrical, there is coordination to be done. If you've got a cabling system that's over 25 foot in length, you need a cable management system per code. If you've got an indoor installation, one consideration is ventilation. Some manufacturers, and this will be marked on the equipment, some manufacturers require ventilation for off-gassing, and there's a specific requirement in code that the manufacturer mark their equipment if that's required. So that's a consideration. And then vehicular protection, whether you're indoor or outdoor, you need a way to prevent the vehicle from coming in contact with the equipment, whether that's wheel stops or bollards or some other protection means. And then accessibility, ADA compliance, that's going to have an impact on pedestrian travel and then landscaping. So there's some site civil components to the installation as well. And then if you've got an installation where you've got public access, revenue generation, revenue metering becomes an important component, as well as our coordination with site lighting. So there's certainly enough to go around in terms of coordination for these types of installations. And as we get into the voltages, there are AC, there are DC chargers. The AC fall into three different categories, but the voltage range is 120 to 600 volts AC. Type 1 is your typical in the garage residential, plug into a 20 amp outlet, and the charger is within that cable length between the plug and the vehicle. Type 2 is your more commercial installation, say at an employer parking lot, where you've got some Chevy Volts plugged in outside in the parking area. Those are typically type 2 installations. And then type 3 is more of a commercial installation that's similar to like a gas station fuel stop type of installation. And that standard is ongoing. It's in flux. It's as the technology evolves, we expect to see some changes there. So that one's still yet to be defined fully. And then on the DC side, which is typically reserved for fast charging, up to 600 volts DC, and you typically see that in installations for shuttle buses or where you've got like a metro busing system. And then I also wanted to touch on automatic load management system, where you can utilize this, say in an existing installation where you've got a limited capacity to add electric vehicle charging stations. You can utilize an automatic load management system to help balance capacity with the number of electric vehicle charging stations you have on site. And then code allows you to factor that in for feeder and for service size calculations as well. And then the other consideration, of course, is source. Where are you going to get power for these electric vehicle charging stations? Whether it's an interior electrical room or an outdoor installation where you've got equipment sitting on pads or unistrut mount, and EMA 3R enclosures. Seen both. And then, you may have ancillary equipment like automatic load management equipment that needs to be housed somewhere as well. So as you consider in an electrical room access to that room, larger pieces of equipment may necessitate the need for very specific requirements to be met. So if you've got equipment that's over 1200 amps, 6 foot in width, so this is large equipment we're talking about. This isn't a small electrical room with a couple of branch panels in it. The larger equipment requires 2 doors, one on each end, on opposite ends. There are some exceptions, and we'll get into those here in a second, but the doors need to have a certain height and a 24-inch width. And if you have double the working clearance, and here's the exception, if you've got double the working clearance in front of the equipment, then you can get by with one door. The code also requires that the door must not impede or block the entry and egress of the working space within the room. So the doors typically will open out. And so this also applies to multiple service disconnects, and that's a change that occurred in the NEC 2020. If you've got equipment that's over 800 amps, you also need to have listed panic hardware on the doors, and they must open in the outward direction.
Okay, so we mentioned, all the code, and I touched briefly on the fact that the NEC is a minimum required established by the code bodies. It's not necessarily the best engineering practice. It's not always what you should just stick to. James mentioned the 24-inch doors. In my experience, going to larger doors is always the way to go. You've got to get that gear in and out. Move-in paths are something that we don't normally think about. We think about the room, right? How are we going to fit it? How's it going to all fit within the room? But how are you going to get it in and out of the room? So those 36-inch wide doors will get breakers out or equipment out or replacement parts. I recommend at least 36 inches wide, double doors, 9 feet high. So that's significantly higher than what the National Electrical Code's asking. In the new code, they start understanding the need to access draw-out devices and not impede that. In my mind, when you've got switch gear, which we talked about being the primary type of system that has draw-out devices versus switch boards, you want to make sure that when those breakers are drawn out, that you can still get past them to one of the other doors. That's just good engineering practice, that you still have clearance, that it doesn't block your access. About the 3.5 feet that's in those tables we talked about, would you really, on some of the bigger 800 amp panels, 1200 amp panels, really want to work in 3.5 feet? Again, those are minimum standards. Unless it's absolutely essential, try and look at 4, 4.5, even 5 feet where you can in primary electrical rooms, not necessarily secondary. You want to be able to get breaker truck access in. Truck access is when you draw out those gears, breakers in a switch gear, and you've got to lift a heavy breaker out and get that out. That also goes through the doors and down the corridor. Arc flash is a whole nother topic, but arc flash basically calculates the amount of energy and then gives incident zones and defines the amount of PPE or the amount of protective equipment that you have to wear based on the zone and based on the energy, incident energy in that zone. So the more space you have, the better for people who are either working or supervising people who are working within those zones. We talked about the height above switchboards, that dedicated space, right? You can go 6 feet or to the structural ceiling. My recommendation is that you should try and get at least 2, if not 3 feet minimum above any major piece of switchgear, any major switchboard. That allows you to get conduits, to get them bent in and out. Yes, I've done pull boxes on top of gear to kind of get past that, but really work with your architects to define the height of that room and get good dedicated clearance above there, and really work with your architect and work with them early in the planning. A lot of times these room spaces are designed before the electrical engineer gets involved, has to be involved during the planning phases. Next. So fire protection, this is also a question. People are like, oh, I don't want sprinklers in my main electrical room. Okay, there's a choice you have to make. The NFPA basically says that sprinklers in a normal electrical room, in a standard electrical room, have to be provided, or you have to put in a 2-hour rating of the main room. So this is a discussion. Usually we do both. I mean, it's good engineering practice. There are a few cities that require pre-action on the main disconnecting service. Those are rare, but I have run into them. They're just simply trying to avoid accidental water. It's certainly a good engineering practice. It's just a lot of money to put in a pre-action or dry type pipes in your main switchgear room. As far as fire detection, you want smoke detectors in your primary electrical rooms. And then in generator rooms, obviously you can't use smoke. You're going to look at heat or flame detections. Next.
So as we get into the electrical rooms, there are specific instances where we need to rate the room, and not all electrical rooms need to be rated. Brian touched on this earlier. The NEC specifically requires that if we don't have a sprinklered building, that the room have a fire rating. I think Brian mentioned that was a 2-hour rating. And then we've got electrical rooms that have dry type transformers that are in excess of 112.5 kVA. If they do not have 155 degree C or higher insulation, they must also be rated. So those are two examples. And then there are some occupancies, specifically NEC high rise and high occupancy, like assembly occupancies, that would require or trigger the requirement for one, approved fire suppression and 2-hour systems be installed. And then NFPA 110, which is the standard for emergency and standby power systems, also imposes some additional requirements in certain installations. The transfer equipment must be installed in a separate room for level 1 systems. So for example, a hospital where you've got an essential system, you have interior generators, and you've got incoming normal distribution, the transfer switch equipment needs to be located in a separate dedicated room, and that room needs to be 2-hour rated. And then interior generators also require a 3-hour rating around the room, and the fuel storage capacity within that interior of the building, within that room, is limited to 660 gallons. It's also obviously important to check with your local amendments or adjustments to code or local interpretations. The national codes aren't always the end-all be-all in every jurisdiction. And then of course you've got insurance carrier requirements such as FM Global, for example, and they may have some very specific requirements that are nuances that you have to watch out for as well.
Okay, I mentioned heat loads. So let's talk about the kind of things that you need to work with your mechanical HVAC engineer on. Is ventilation required? Generally speaking, the rating of equipment, particularly sophisticated switchgear with electronics and controls, you want to keep no more than, you don't want it to exceed about 104 degree Fahrenheit. It's different for outdoor type rated equipment, but for the indoor rated gear, above that, you can start to have errors in measurement systems in sophisticated relays. So really, when you're talking to your HVAC engineer, you first need to establish the fact that whatever we do to this room, we need to keep it below 104 degrees. Now, second thing is you don't really want your maintenance people working at 104 degrees or 103 degrees, right? So there has to be some reasonable discussion, particularly if they're critical large power rooms, what would be a maximum temperature that you would want maintenance and operations people to work in. Maybe that's 80 degrees, maybe it's 78 degrees. Again, it's a discussion with the client and their maintenance staff as well. So we generally recommend about 86 degrees maximum average, but it may be lower or higher. So where's the heat coming from? It's coming from the transformers, as I mentioned. There's some rough rule of thumbs. Use this in the beginning planning stages, but please get the cut sheets from your actual vendors as you're specifying this to get these. But without a transformer, you can put in about 1 cubic feet per minute per square foot. When you have a transformer, 1 to 2% of the kVA is rejected into heat. Now they're getting more efficient these days, but 3 CFM per kVA. Again, these are rough rules of thumb. Generator rooms is a whole nother issue and there are whole presentations on generator room design and generator room considerations. But we have, you have to understand cooling versus combustion air. The generator has 2 sources of air when we're talking about indoor locations. Those big louvers that are coming in and the big radiator, typically most of that air is for cooling. So for instance, if you were to remove the radiator and put it just outside the room out on grade, you can decrease the louvers significantly in the amount of air you're bringing, because the combustion air is what remains and the radiated off the engine itself, but most of that's going through the radiator. You have to look at how those louvers are opened and closed. You want to look at the cold or hot climate, and when those come on, you certainly in a minus 10 degree Fahrenheit don't want to open up initially all the dampers. You might want to phase them open so you don't get the all the cold air coming in and freezing the room down before the engine heats up. And a general rule of thumb is that an engine generator will put off about 2,500 BTU per hour per kVA. These are terms that are helpful to discuss with your mechanical engineer. Next. So battery UPS rooms. This is another area where these are even more temperature sensitive, particularly in the traditional lead acid, valve regulated type batteries that are still being used quite frequently. Those have to be kept at about 77 degrees Fahrenheit max. That's because the life of the batteries will decrease significantly if it gets warmer than that. So watch the temperature on those rooms. A lot of the old inspectors and a lot of the old codes are concerned about hydrogen. We talk about a lot, you see a lot of discussion about hydrogen removal, ventilation systems. Typically the sealed batteries that are used today don't require this versus the old flooded ventilated batteries that you see sometimes in some facilities. Again, this is going to be a discussion with the local authority. Most places say batteries are batteries and I want fans and a hydrogen detection system in there. Review that with your HVAC engineer. Now, lithium ion batteries are newer. They're coming down in price. They used to be a pricey option, but those have a whole nother set of requirements. They are better at higher temperatures, so that's a plus. They last longer, but there's new codes and conflicting codes coming up on the safety of lithium ion batteries and the potential for explosion. So work with your fire protection engineer, your code engineer. The general safe rules are 1 CFM per square foot. And if there's a ventilation fan in there, make sure there's a fan failure relay so you know if the ventilation in the battery room has failed. Next.
So one critical aspect of coordination that is often overlooked with electrical installations is our coordination efforts with structural. I mean, we're putting in switch gear and switchboards and generators. Often this equipment is on upper decks. It's up on upper floors, can end up on the roof in a roof penthouse, for example. And these items weigh, in the tonnages. So it's important that these things be accommodated accurately, that the load-bearing capacity is within the structural system. It needs to be coordinated. Also, vibration isolation. An example would be a sensitive building where you've got sensitive adjacencies to the electrical gear, like research facilities, animal research facilities, vivarium spaces, those type of buildings, where you've got concerns about the vibration, basically leaking from equipment and traveling through the structural system into other occupancies. It's important that we isolate that, we coordinate that with structural. Of course, in computer rooms and raised floors, those things need to be coordinated with structural. Where you've got housekeeping pads under equipment, that adds weight. Penetrations, especially where you've got very tight floor to floor on projects and structural members, that are supporting the upper decks appear to be in your way. I mean, trying to make a path for your conduits or for cable tray, etc. Those penetrations need to be carefully coordinated with the structural engineer on the project to make sure that we're not penetrating and causing an issue with the integrity of the structural system. Of course, fire sealing, and then the path of delivery, where you've got multiple conduits, a conduit bank running through a building that's suspended, for example. These things add significant weight per linear foot, and it's important that we have that fully coordinated with the structural engineer on the project. Wanted to just briefly walk through a case study, an example project that we recently completed. This is a Franciscan St. Anthony's Hospital. It's a greenfield hospital that went up in Michigan City, Indiana. The building was 450,000 square feet. It was a 5-story building that included a penthouse on top, so it was 5 occupied floors. It was not classified as a high-rise building because we came just under the 75-foot tall threshold, so we were able to avoid some of the high-rise requirements in the project. This was a developer-led design build delivery model for the project. The building had 3 1.5 megawatt 480 volt generators located interior to the building, and had 4 main 5,000 amp double-ended switchgear lineups. So we had some big equipment in here. Next slide, please. So this is an example of the main electrical room. So we had the main electrical room and the main essential system electrical room. You can see that we had them separated. The automatic transfer switch equipment being in the essential side, and then the incoming electrical services on the normal side. So we kept separation, and this was located on the lowest level of the building. And then, like I mentioned previously, we had 3 generators on the project that are co-located within the generator room. We had the 3-hour fire rating around this room, and then adjacent to that, we had paralleling gear for the building, which required both front and rear access. And then I just wanted to give an example too of the typical electrical rooms that we saw on each floor that were stacked vertically to provide ease of conduit routing throughout the building. These were located close enough such that the 120 volt circuits that were coming out were limited to approximately 100 lineal foot to minimize voltage drop in the system. And you can see once again that now this isn't a code requirement, but it's a good practice is to keep the essential system and the normal system equipment separated. So we had 2 separate closets in each area of the building.
All right, awesome. Thank you for all that terrific information. Thank you to these subject matter experts, James Lessard and Brian Renner, for this presentation.